We're going to look at continuous probability. And first, we're going to start with just kind of looking at a picture. And we'll start with this notation with function notation, or f of x, is going to be our probability density function, or PDF for short. And that PDF, that function, is going to help us find the probability, but it's not the actual probability. So when you're graphing the probability density function, so let's just say that we have our x-axis and our y-axis, which we're going to call f of x for our function. And any particular function, as long as it's a function, so let's say that I have some function, some curve that goes like this, and rather than going from negative infinity to positive infinity, which you could, I'm just going to stop it at this point A, and I'll go ahead and stop it here at this point, we'll call B. Any arbitrary points. And x could be negative or positive, but the function has to be positive. In fact, that's one of our properties that we need to meet to make sure something is a valid continuous probability distribution, is that the function itself is positive. It could be 0, greater than or equal to 0. So we have to be above the x-axis for the function. The x itself, though, could be negative or positive. And we don't have lines coming down for our function, but you can kind of imagine that there are some vertical lines coming down at our points. And if we were to look at the total area under this curve, for this to be a valid probability distribution, this total area under the curve itself, so I'll put in blue here, roughly, above the x-axis, below the function between A and B. It could be a limit if it's out to negative infinity or positive infinity. But that total area, that's the second thing that we're looking at, that has to equal 1. Now, for calculus, we look at that as the integral from negative infinity to infinity, where a function is defined, of our PDF has to equal 1. And that'll help us in the next example when we're trying to find, say, a constant, something like that. Now, looking at any one particular value of the function, so let me go ahead and erase this area. Thinking about just a single number. Let's say I have a constant, which I'm going to call x in here. Well, let's actually make it a number itself, like 4. So let's say we'll call c a constant, and for this case, it's equal to 4. And if I wanted to actually find the probability of any constant, there is no area on the line itself. So if we were to thinking about just the vertical line here, there's no area, and we're going to equate probability with area. So what would this actually equal then? The probability of that constant, whatever that might be, like the value of 4, whatever constant, is going to be just equal to 0. There's no area in there. So we're going to be looking at the area under the PDF as our probability. A little bit different than we were working with our discrete probability distributions, because f of x, we were talking about that probability mass function, we were plugging in a value of x and getting a probability out of it. But in this case, we need to actually be looking at the probability between 2 points, below a point or above a point. And so, for instance, if I was wanting to find the probability that my random variable x was, say, less than or equal to a constant, say 4, well, I would be then looking at the area below 4 And, thinking about it does go to negative infinity, but below a, the function is just going to be represented as 0. So there's no need to go to negative infinity. We're just going to stop at whatever that lower boundary is of a. And that area in there that we have shaded would be your probability. So when we're talking about this, we're looking at the probability of a big X. Our capital X is our random variable, and the little x value in this case is equal to 4. So sometimes you'll see it as probability of X equals little x, where in this case, the little x is equal to 4 itself. In a class where we don't require calculus, usually what will happen is you will use software where you have a program that will already find this probability for you. But in our course, we should know that the probability of x less than or equal to x, also denoted as capital F of x. So it's just because we will use it a lot and just for shorthand, we like in mathematics to just make things a little bit shorter. But that is called the cumulative distribution function. And we'll use CDF for short. In fact, a lot of the, like say TI calculators, you'll see the PDF and CDF shorthand in there. And usually we're using the CDF when we're talking about our continuous distributions. But if you have calculus and know what an integral is, then our f of x is equal to from negative infinity up to whatever value of x that you're trying to find here of f of x dx. So that's your mass function. And sometimes if you're working with certain distributions at a course that doesn't require calculus, they will give you this function already. So all you have to do is plug in for x and you would actually get a probability out. But usually it's the probability below a point. So do be careful, because if you're trying to find the probability, say, above a point, you might have to actually take the complement, for instance. If you're finding the value between 2 points, you might have to find 2 probabilities and subtract the smaller probability from the larger probability. Now note that these are probabilities still, so your answers should be numbers between 0 and 1 or 0% to 100%. So for an example, a kind of very standard homework question is that you might actually have to find a constant k to make something a valid continuous probability distribution. So let's say that we have a random variable x. With the following probability density function. And we're going to use piecewise notation in here. So we have f of x equals, and then there's going to be 2 pieces that we're looking at. The first is the function that we're going to define between 0 and 1. We're going to let k be some constant that we don't know yet. We're going to try to solve for k minus 2 times x. For 0 less than or equal, so let's do strictly less than x less than or equal to 1. And then 0 elsewhere. And this is an important thing too, is that when we're looking at, say, less than versus less than or equal in an area, if we stop at the point, if we include the point or not, so let's say we went up to that value of 4. In a discrete distribution, say we had the integers, we were looking at, say, 3 to 4, there's a huge gap in there, and there's a jump in there. In a continuous distribution, you could have 3.9999999 for your value and still be less than 4. So when we're talking about strictly less than versus less than or equal, we'll find the same area in a continuous probability distribution, which is a lot different than our discrete probability distributions. So I'm going to split this up in a couple different questions in here. So let's do part A is find the value. And I've said it, but I didn't write it down. K is a constant. right? So part A is find the value for the constant k. So that this is a valid PDF. So to do that, we need to look back at our PDF, the kind of the rules in there. The function itself has to be greater than 0. We could graph it too if you wanted to. We don't have the constant itself, so it's a little bit harder, so we'll wait on that. But we do need that the total area has to equal 1. So our from negative infinity to infinity of f of x dx has to equal 1. Our function itself is going to be only really of interest between 0 and 1 because it's 0 everywhere else in there. And so if I'm just looking between 0 and 1, this becomes the integral from 0 to 1 of f of x dx. That function that we're only interested right now is this top portion because it's just going to be 0 everywhere else. So we're going to say of k minus 2x dx, and we have to set that equal to 1. So that's our goal. So first I'm going to integrate, then we'll set it equal to 1, and then solve for k. So if I just integrate the function, well, first of all, I can bring k right out in front. So integrate the k, or sorry, distribute the integral through. So I have the integral of k dx minus the integral from 0 to 1, 2x dx. And there's different ways that you can go about that, but this is just a really quick way to do that. So what do we get here? This first piece in here would be kx, and the bounds from 0 to 1, minus, and then our 2 would cancel when we take our 2 out in front. So we would get just x squared from 0 to 1. When we plug in x equals 0, we would just get 0. So really this comes down to just k when we're plugging in for 1. So this is just equal to k. And again, when I'm plugging in for our x squared value, x 0 squared is just 0, 1 squared is 1. So we just get a minus 1 here. And then we're going to set that, okay, we're setting that equal to 1. And then just solve for k. Super easy there. We just have to add 1 to both sides. So our k is going to equal 2. So the function between 0 and 1 is going to be equal to 2 minus 2x. So let's sketch a graph of that. Do that as part B. So recall that the function is 0 everywhere else, just not between 0 and 1. So this is going to be a little triangle. If we were plugging in, here's it 1, 1, 2. There's my function. There's my x. If I were to plug in f of 0, I would get 2. If I were to plug in, it's a line, straight line. So at 1, I have 0, so I have a little triangle. So it looks like that. So then if I actually were to use a triangular distribution like this, oh, and 0 elsewhere. So we also have these lines that go from here. And that would be actually an open circle there and closed circle here. So it would look like that. If I wanted to find a probability without even using calculus, then I could find any value of, say, x in here And area below or above, I could simply do the area of a triangle and then take the complement if I needed to. And it'd be a lot easier than finding the integral, but we're going to go ahead and find the probability mass function and then use the probability mass function to find our area. Let's see, part C. We're going to find a CDF, a cumulative distribution function. We can recall that that function f of x is from negative infinity to f of x dx. So if I'm looking at our particular function, our f of x will be equal to, now we don't really need to go all the way to negative infinity, we just start with our lowest point of value, which is at 0. So we're going from 0 to x of 2 minus 2x dx. All right, so we would integrate that. So we would get 2x minus x squared going from 0 to x, which is equal to the 0, when I plug it in there, is just going to cancel out. So that's just equal to 2x minus x squared plus some constant. We can ignore that for right now. And then what we're going to do for our function itself, our cumulative distribution function, really should be always ending at 1, because we have a cumulative area. We start at 0 always, and we end it at 1. And so how we write the function will be like this, pieces. So we're going to have 0, the function itself is equal to 0 for all values of x that are less than or equal to 0. And then we'll have this 2x minus x squared for all values of x that are bigger than 0, but less than or equal to 1. And then our cumulative distribution function will equal 1 for all values of x that are greater than 1. And if you were to graph this function, so here's 0, here's 1, that long. But this piece at 1, 1, we have a dot there. And at 0, 0, we have a dot. And then we have this upside down parabola. Let's come on up here like that. And then after 1, it's just at 1, and below 0, at 0. It looks like that. Then we can use that function. There's actually 2 ways. So we can find the probability, say x is less than or equal to 0.25. So we could evaluate that CDF at x equals 0.25. Well, that would just be 2 times 0.25 minus 0.25 squared, which would be equal to 0.4375. Now, if you didn't want to go through the process of finding the cumulative distribution function and you already had the PDF function, so recall our little f of x was equal to the PDF at a certain point, we could find the integral from 0 to 0.25 of that little f of x function, and it would also equal 0.4375.